3.8 Inverses, video number 2. So this next question asks, how do composition of functions relate to inverse functions? Well, we learned in our composition of functions, we had an example in the last section where when we found the composition of two functions, we got x, and then when we did the composition in the other order, we also got x. And we said that means that those functions are inverses. If you don't remember that, that's okay. We're going to write it down right here. So what we learned, we just did one example in the last section, is that if f of g of x equals g at f of x, and they both equal x. So not only do the composition of the functions have to equal each other, no matter which order we do them in, they also both have to equal x, then f and g are inverses. So the definition says that f and g are inverses if and only if. IFF is a shorthand version of if and only if f at g of x equals g at f of x, and they both equal x. So in order to prove, as we're going to do in example 4, whether f and g are inverses, if they are, I have to show that when I put g into f, I get x, and I put f into g, I get x. I have to show that they both equal x, which therefore makes them equal each other. So let's see. Let's start off by calculating f at g of x. So I'm going to take this and put it right there. So I get 3 times negative x minus 2 divided by 3 plus 2. All right, these 3's would cancel, and I'm left with negative x minus 2 plus 2. And I get negative x. Well, right there, I've already proven that they're not inverses, because if they were inverses, they're going to have to equal each other, but they have to equal x. So I can say f at g of x does not equal x, therefore f and g are not inverses. Yes, this is a proof. These are not geometry proofs. These are what we call algebraic proofs, where we use algebra, substituting one function into another in order to prove something. But we have to state why we know they're not inverses. And it's because f of g of x does not equal x. All right, so let's go ahead and let's graph the inverse of this above function. So when you're simply given a graph and you're asked to graph the inverse, the best way that I have found to do this is to label the key points. And list their ordered pairs. So I would have -6, -4. And this is the original. I want to say that these are my original points. And then -4, 1. Then 2, 1. 6, 5. And 8, 2. then what I'm going to do is I am going to find the inverses. And as I do that, I just want to first of all note that the ordered pairs I put in the order that they were to be connected. So I didn't say -6, 4, and then give the ordered pair to 1, because that would mean I'd connect it to there. So I'm saying this because as you list the inverses, you also have to connect those dots in the same order. You can't just connect them in any random order. So the inverse here would be -4, -6. So -4, -6. The inverse here would be 1, -4. So 1, -4. And I want to connect as I go. I don't have to use a ruler. I'm going to go ahead and use a ruler. I'm just not real great at drawing straight lines freehand. Okay. And then 1, 2, 1, 2. Then 5, 6, 5, 6. And then 2, 8. Now, one of the things I want you to note that when you're doing this and you are wondering, I wonder if I graphed it correctly, one of the ways you can tell if you graphed your inverse correctly is that the graphs of inverses, and we'll write this down, the graphs of inverses are reflection, sorry, that's an L there, are reflection symmetric over the line y equals x. Right? So if I was to draw this dotted line through y equals x, they are reflection symmetric. That's how I can tell that I have graphed them correctly. If they reflect over that line, then I know I've graphed them correctly. All right, so let's look at Lesson Master 3.8. It says a function is described, give a set of ordered pairs or an equation for the inverse of the function, and then state whether the inverse is a function. All right, so let's start with number 1. So I'm going to, this space right here can be used from doing my work. So first of all, number 1, I'm going to switch x and y. So I have x equals 2 minus 3y. I'm going to solve for y. So I get x minus 2 equals -3y. I'm going to divide everything by -3. So I get that y equals, that would be, I could leave it like that, or I can say -1/3 x plus 2/3, because this -3 is distributed to both. So y equals -1/3 x plus 2/3. And I know that that's a line. And a line is a function. So yes, the inverse is a function. Number 2. When I switch x and y, I get x equals 1 over the square root of y. I know that I cannot solve when y is in the denominator. So I'm going to multiply both sides by the square root of y. And I get x times the square root of y equals 1. I'm still trying to get y by itself. Now I can start doing that because y is up top in the numerator. So I'm going to divide both sides by x. I get that the square root of y equals 1 over x. Got to get rid of that square root, so I'm going to square both sides. And I get y equals 1 squared is 1, and x squared is x squared. So y equals 1 over x squared. And that's one of my parent functions, so yes, I know that the inverse is indeed a function. For number 3, I just have ordered pairs, so I'm going to list my new ordered pairs. I'd have 2, 3. And I'd have negative 1, 2. I'd have 3, 5. And I'd have negative 1, 3. I notice right away I have an input of negative 1 where I get 2 and an input of negative 1 where I get 3. So this is not a function because each input should have only one output, and negative 1 has an output of both 2 and 3. Right, now let's look at number 4. And I'm going to switch x and y. X equals 3 over y plus 4. And I can't solve for y as long as it's in the denominator, so I'm going to multiply both sides by y plus 4. Multiply this side by y plus 4. Here the y plus 4's cancel. And this x is getting multiplied by y plus 4, so I get xy plus 4x equals 3. The 4x can be moved over because it doesn't have a y with it, and I'm trying to solve for y, so I need to get y alone. So xy equals negative 4x plus 3. You can say 3 minus 4x. I just always put my variable first and then my constant. Solving for y, so I'm going to divide everything by x. So I get that y equals negative 4 plus 3 divided by x. Okay? So y equals negative 4 plus 3 divided by x. Now, in trying to figure out if this is a function, I can simply look back to this, and I know that this graph is going to look like that. It's going to be shifted, but that's the general idea of the graph. And does it pass the horizontal line test? It sure does, so it's a function. Right. The next one, next part down here, determine whether the inverse of the graphed function is a function. So I'm going to use the horizontal line test because these are the originals. So I can predict about the inverse. Does this pass the horizontal line test? Yes. So the inverse would be a function. So this is not the graph of the inverse. This is the graph of the original. How about here? Now when I get here, right there, it does not pass the horizontal line test. So inverse would not be a function. And for this one, I look good, so the inverse, it passes the horizontal line test, inverse would be a function. Okay. And now you can do the other 3.8 lesson master using this one to help you.